So hello friends, and today we shall be doing our first deep neural network model, and that will be on MNIST dataset. This is a modified National Institute of Standard and Technology dataset, which is a Hello World dataset of computer vision. And this is, if you want to acquire this dataset, you can go here, go to the data, to the Kaggle website. I'll provide the links, and you can simply go participate in this and download the sample test and train dataset here, or else we'll be downloading it directly from the Keras, the deep learning library, which works on TensorFlow. So all the details during our practical session. But just to give you a detail about this digit recognition dataset is that it contains a record of like 60,000 or so digital images, and these digits are from 0 to 9, written with in different unique way, because it is handwritten and different people have different handwritings, and you can see here the different ways. And the neural network have to really learn the way how to differentiate one digit from the another and give you a good prediction, a good result with minimum loss. So you identify digits from the dataset. This is what we want. And this MNIST dataset was released in 1999. And since then, it has been widely studied both by researchers and the learners. Now I will come to the Jupyter notebook. And what you do is, this is my directory in which I'm working. And you upload new Python 3. And in that, you can just rename it as like dataset of your choice. So I can just write here MNIST digit dataset, okay, or recognition dataset. The spelling is wrong, but okay, I can just correct it. It is MNIST. Okay. So what I do is I start with importing basic libraries, and what I do is I import the NumPy as NP, and because this will do all the linear algebra calculations for me, and it is really very helpful in understanding most of the things which we will discover later. I will use this matplotlib as PLT because this is for, I will show you the images here, and from keras.models I will import sequential, because we will be building the models, and the basic model we will use is sequential. And again, from keras.layers I will use, or I will import dense layer because I'll be using dense, and also from here I will use activation. This function is also there. And from, this is from, okay, keras.utils. So this utils is very important because it will help me to convert my data also again. So I will tell you, it has many functions. So I will take this from utils, I will import np utils, and now I want my data set. So from Keras only I will take my data set. So keras dot datasets I will import MNIST dataset. Okay. So another thing which I want to show you is that when you run this dataset, do you run the cell, and okay. So this has been done without any problem. So it has been compiled, it is run. Now in this data set, since I'm importing it from Keras, it has been stored as Xtrain and Ytrain format, and also it is stored in the form of Xtest and Ytest. So this is the standard way of writing it, and here I will load my MNIST dataset, MNIST.load underscore data, and all the data set will be loaded in the format of Xtest, Xtrain, Ytrain, and Ytest, Xtest. Okay. Now, just for your convenience sake, I will just print the shape of the data. Okay. So let's see the shape of the data. So what I do is I will print, and here I will do Xtrain, and later on I can just come and change the values in different rows and dot shape. So that is what I want. And now here I would just simply come and do here y-train. Here is x test. Okay, here is x test and here is y test. Okay, and here is y test. Now here is x train shape, and now we change things here also. Y train, y test, and here you change it to entire this thing, and that is your y test. Okay, so this will give me the shape. So now you can see the shape of my data set, how it looks. So x train is in the form of 60,000 images, and this is 28 by 28. So what is this 28 by 28? When you see this image, you see this 5 digit. This is in the form of 28 by 28. The resolution is 28 by 28, and this is what it is showing me. And so we have like 60,000 images in this format. Okay, so in my x train I have got some 60,000 data images, and in y train I have 60,000. X test I have 10,000 to be tested upon, and in y test again it has been segregated to 10,000. Very standard data set. And now this shape has to be looked after before we give it to the neural network. We train the model and so on. So let's see what we can do with this. Now another interesting thing which I want to show you is, let's see one of the images. Okay, so what I do is like plt.im show, and in this I want to show you the x train on the image of the 0th element, or which occupies that place, and you can see that this is the image. By the way, this MNIST dataset is in black and white format. It is not colored. So what you do is I'll show you two more things here. So what I do is plt.im show, and here let us see another image at different place. So I'll just take 4, and in this I will use, now I want to show you the real image, right, and how non-colorful it is, or how much black and white it is. So what you write is cm.binary, and I will use the semicolons because I don't want this MNIST matplotlib access and stuff. So you can see this image. Now this is the image format which we understand. Now how does this machine understand this thing? Let us also understand this, that how it is being stored. So I just write, I will take the same digit, same place 4, and I just show you the data. Now this is something we got tensors, we got multi-dimensional arrays, and this is what tensor is, and you're working with tensors. Now tensors are also fundamental units, I would say, and vectors are derived from these tensors. These are multi-dimensional arrays. Now you see here multi-dimensional arrays, and the first, second, third, fourth, fifth, sixth arrays are all 0, and the real value starts from like this array. It is from the range of 55 to somewhere around 148, right? And then you followed by 0, 0, 0. So you can see the range, that it varies from lower value to the higher, and it must go to till 255 because the highest pixel is still 255. Okay, and we must be having 255 here. Yes, we got it here. Okay, and now if you see that how these arrays are being created, so you just look at this image. I'll go with the black and white one, this 4th one. So you look at this image, okay, and you just scan through this entire row, entire this thing, you will not find anything. So that's why that array has an entire array is 0, and here also entire array is 0, and we continue this till like 5 or 6 arrays, and then we start getting values, the pixels of it, and we can see it stored in array. Okay, so this is how the digit is being stored, and it stores in this numerical format. Now another thing to notice here is that we have got a wide range, and we would like to reduce these range in certain predictable formats so that it becomes easy for a neural network to train the model, and it really reduces the computational cost also. So now let us deal with standardization or scaling of our data set. I will normalize the data, and there are 2-3 things we'll be doing together here, so just follow me closely. So what I do is I will write here x train equals xtrain dot as type. See, I will be converting them into the floating type, or you can use the integer type also, but since 32 is being used because this is the standard size and the RAM gives it a good space and memory in your RAM. So, and we convert it into floating because this then it becomes easy for a neural network to learn this. So I have converted this train and test data into the np.float by using numpy into float, and then I will be reshaping this dot reshape. And since we know that we have got it in tensor, that is three-dimensional something, so we want to reshape it in some vector format. So we get 28 into 28 that has been reshaped. Now I want to scale down to in the range between 0 to 1. So what I do is I will divide this by 255.0. Okay, and the similar thing I will do with x test, because these have we have seen that these two have got different shape, and so we are just reshaping it, we are scaling it, and we are converting it, okay, just to make it more presentable to the algorithm or our deep neural network. Now I would just show you one more thing. Let's see the size. Okay, let's just see the print x train and dot shape, and what you do is here, just come here and change this x test, and let's see. Okay, so we have got some, like, in two-dimensional space, a very nice figure that is like 28 converted into 784. If you just multiply it, you will get the same thing. So this is just mathematical calculation which we are doing, manipulating data, but it remains the same. Now I will go to y. Let's do something with y also. So what I do is I will just go here, and y train equals to, again from this y train I will take it as s type, and let's do this. It's a good practice that you just convert this into 32 np.32 and then copy paste it and do the same with y test also. And we just do this and just change this to y test and y test as type np dot this thing. Okay, but remember this thing, I have just changed the type. I have not done anything with the size or the shape of the data set. So if you just want to check it, so just check it dot shape and it will remain the same. Okay, 60,000. Okay, now we have to do something with this so that it just fits the data, and it can really, the neural network can really work on it when we compile it. So I have to make it also two-dimensional. So how would I do that? I will simply write here xtrain, and here I will write np dot utils np underscore dot to categorical, and now I will write here y train. Okay, and what you do is you just simply copy this, paste this, and here write y test. Okay, np.utils to categorical y test, just write here y test. Okay, be careful here what you are manipulating and what not you are manipulating, and just run this. So now what you have, just let me just check the size. Okay, so let's just check the size of this. So I will write here print y train dot shape, and here let us write here test dot shape. So can you see this has again been converted into a same similar format for like we have for x train and y test, right? X test and y test. Now we come to the model building, the main thing of this video. Let's just come to the model building process. So I just add few cells here. I'm trying to add a few cells. We'll build a very basic model, very basic, since it is the start. So we'll build with the sequential model, and now we shall start adding the layers dot add, and I will add dense layer here, and now you have to give in the neurons. I will take 100 neurons And the activation, you can change the neurons as per your like. Activation, I will take ReLU. This is rectified linear unit and improvement of linear activation, this thing, rectified linear. And we have got various variation of ReLU also, leaky ReLU and softmax, and there are various activation function, and they just help to trigger your input above a certain quality. It does not let your neuron die. So that is what we are trying to do. And ReLU is by default, it has been used, it is good, so we'll use it. You can use different activation functions here. I will add another layer here, and that will be our output layer, and this would have 10 neurons. Now this is very important to note here, that I will use activation as softmax, because this is generalized, or I can say generalization of log regression, logistic regression, and it can be applied to continuous data apart from classifying binary. So it is a good activation function. Now I will just want to tell you also that the output layer, it has the number of neurons. How would you decide the number of neurons on this? It depends on the digits we have here. We have it like 0 to 9, so we have got certain like 10 digits, so we have got 10 neurons in our output layer. Okay, if we had it like 0 to 11, we could have got 11 digits or so. So that is what makes our output neurons decide on how many output labels we have, right? So now we will compile. You compile this model, and we will pass certain parameters for that. So for that, we will have this model dot compile, and we will write here loss, because we want to minimize the loss. That is what neural networks are. They are worried about loss. We will use here categorical cross entropy, and you can use binary or sparse cross entropy, but I will use here this thing, and the optimizer would be Adam. By default, we use Adam. So these optimizers are nothing but these are algorithms or methods which help you control the weight and the learning rate. You can use stochastic gradient descent, but Adam is best because it gives you good performance, good, very it is very fast actually. So now we go to the matrices, and the matrice I would use a simple accuracy. Okay. So this is the basic model compilation. I can give more parameters, but I don't wish to. Now I will write here model.fit. Let's fit the model, and we want to fit what? Let's fit X train, let's fit Y train, and they are of the same size, so they are easy to go. And then we have epochs, and epochs are the iteration. That means each pass on my entire data set, and can improve the accuracy or reduce the loss. That is what I'm concerned about, reducing the loss. Let's run it. You can increase the epochs to 5, 10, but that just adds to the computational cost of your processor, and your system might crash or hang if you really increase the epochs and neurons. So try to strike a balance, and this will come with practice. So you can see that this has been run, and my loss is for first one, it's first epoch, it is 0.2, and the accuracy is 92%. Loss for the second epoch is 0.12, and the accuracy is 0.96. And for the third epoch, it is reduced to 0.08, and my accuracy is 97%. So this is good. The losses is being reduced. So I can try it with 5 or 10 epochs also, but I am not interested right now. Okay, so now I want to tell you something about let's just try this on our test data set. How is it performing? And I will just take here value loss, value accuracy, and I will write here model dot evaluate. Okay, and what will you evaluate? I will write here X test and Y test. Right, I want to evaluate it on Y test, X test, and just print it. Print the value loss and the value accuracy. Right, okay. So this has come out to be the loss is like greater like 0.90 as compared to my previous loss, which was 0.85, which is good because it is not replicated or overlearned. I can infer this. And the accuracy is like 97.4. Here it is 97.2. Fair enough. Okay, so this is what it is. Now we are not still sorted, we're not still done, because we have to work with the predictions. Okay, so what I do is we will make an object called predictions, and in that I will write here, I will give my model dot predict. Okay, what you want to predict, it takes a list, so just mention this thing in your list, x test, and print the predictions. Now here is coming something really interesting. Okay, now you got these predictions of x test. Can you understand these multidimensional arrays, these tensors? Yeah? No, even I cannot understand, because this is something that has the network knows what it means, but we don't know what it means. So what I will do is I would simply use NumPy for this to understand how to infer and what is it really saying. So NumPy will help me give me a number, for this entire thing. And I will use here argmax, and here I will give predictions, and let's see what is there at the 0th prediction. Okay, let's see, 7. All right, fine. So if you want to check what is there in at what position, suppose I want to check the digit here, predictions, and I specify a place like 6. Let's see what digit is there. So it's 4 there. Okay, so this is how you really check the predictions in a human readable format, and this was something called machine readable format. Okay, so I can also try one more thing here, like, so print.np.argmax predictions. Okay, 4616 something, that has just returned me so much of these things. I just write here 9. So and 9 position, at 9th element you've got some digit named 9. So this was about deep learning neural network, basic neural network with Keras. And this Keras library is handy when you want to make deep neural networks or perform some neural network projects. And this works under the backend is TensorFlow. It uses Theano or TensorFlow. And you have to install this Keras before you start doing this. So you can just simply write, if you're working it for the first time, so you can just import it in your this thing. You can simply write here, since I've already imported, just write here pip install Keras. Okay, so your library would be imported from your package from where you have done it, and you can start working with this library. It is a good library for deep learning. It is quite fast, since it wraps the TensorFlow maths library and takes the functionality of TensorFlow and applies it here in your dataset, and the calculations are really fast and it makes good predictions. Okay, and we have seen it. So this was a basic dataset which is there for understanding computer vision, how to do digital recognition, and then we can move on to image recognition and so on. So if you're interested in more projects like this, please comment in the comment section. I can come up with Cypher dataset and much more. And write yes or no, give a thumbs up. And activation functions, like we've got various 10, like approx 10 activation functions, ReLU, softmax, hardEd, 10edge, tench, and much more. So I can come up with that. I can come up with layers, and there are various important things in deep learning theory to understand before we jump into the practical session, but we have done the practical session first. So these are matrices also, which you can experiment. There are optimizers also, which we can experiment, and the loss function also. So, and there are pros and cons, since there are many. So just let me know if you want a detailed description of all these. optimizers, loss functions, matrices. The things which we are using here, you have to be very uh, careful about what we are using here. I'm using ReLU here, I'm using softmax here. Why haven't not used sigmoid function here or sigmoid activation here? Because it has got its own drawbacks. That's why I have not used sigmoid, I have used softmax. So if you want the drawbacks, pros and cons, a little theory about it, let me know in the description box. List all the links I will be providing so that you can, of the Kaggle and the other sources, so that you can go ahead and see things which will be simplified. So that's it for this video, guys, and thanks for watching.